Welcome back, inspectors, engineers, quality professionals, and future Level 2 and Level 3 certification candidates. Today we are starting Chapter 7 of our NDT training series, and this chapter focuses on leak testing, commonly known as LT. Now, before we begin, I want to ask you a simple question. Have you ever seen a leaking valve, a leaking flange, a leaking pressure vessel, or maybe a heat exchanger tube leak during operation? Most of us have. But here's something interesting. When you see fluid coming out of a system, you're actually seeing the final result of a much larger scientific process involving pressure, molecular motion, fluid dynamics, and containment integrity. Many people think leak testing is simply spraying soap solution and looking for bubbles. That is one of the biggest misconceptions in NDT. Leak testing can range from a simple bubble test all the way to highly sophisticated helium mass spectrometer systems capable of detecting leaks measured in parts per million. And in industries such as oil and gas, aerospace, nuclear power, petrochemicals, pharmaceutical manufacturing, and semiconductor production, leak testing is absolutely critical. A small leak can lead to product loss, environmental contamination, equipment failure, production shutdown, or even a major safety incident. Throughout this chapter, I will explain not only the theory required for certification exams, but also how leak testing is actually applied in the field. And pay close attention, because several exam traps appear repeatedly in ASNT and PCN examinations. Let's begin. Before starting any technical subject, we need to understand what we are expected to learn. By the end of this chapter, you should be able to confidently define leak testing and explain its industrial purpose. You should understand the difference between a leak and leakage. And trust me, this sounds simple, but it is one of the most commonly misunderstood concepts among certification candidates. You will also learn pressure fundamentals, vacuum fundamentals, leakage measurement concepts, static and dynamic leak testing, open and sealed system classifications, and finally, how to select the correct leak testing method for a particular application. Now here's a practical question. Imagine you are working as a QC inspector on a newly fabricated pressure vessel. The client asks, which leak testing technique should be used? Can you answer immediately? Probably not, because the answer depends on required sensitivity, accessibility, cost, safety requirements, equipment availability, acceptance criteria, and operating conditions. This is exactly why technique selection is such an important topic in leak testing. By the end of this chapter, you should be able to make those decisions confidently, and not just for exams, but for real industrial situations. Let's begin with the fundamental definition. Leak testing is concerned with the flow of liquids or gases from a containment system under pressure, or into a containment system that is under vacuum. Let's break that down. Imagine a pressure vessel operating at 10 bar pressure. Inside the vessel, pressure is higher than outside. If a hole exists, fluid will attempt to move outward. Now imagine a vacuum chamber. Pressure inside is lower than atmospheric pressure. If a leak exists, air will move inward. In both cases, leak testing is concerned with detecting that movement. Now, many students ask, why do we perform leak testing? There are three major reasons. The first is preventing material loss. Imagine a refinery losing expensive process gas continuously through leakage. Even a small leak can result in significant financial loss over time. The second reason is safety. Imagine a leak involving hydrogen, natural gas, ammonia, hydrogen sulfide, or chlorine. The consequences can be catastrophic. The third reason is reliability. Leak testing identifies components that cannot maintain their intended containment function. This is particularly important in aerospace, nuclear, military, and oil and gas industries. Remember this. Leak testing is not merely about finding holes, It is about ensuring containment integrity. And containment integrity directly affects safety, reliability, and profitability. Now, inspectors, this slide contains one of the most important exam concepts in the entire chapter. I want you to pay very close attention. Let's discuss the difference between a leak and leakage. Many students use these terms interchangeably. That is incorrect. A leak is the physical opening itself. It could be a crack, a pinhole, a fissure, a void, a crevice, or any pathway through which fluid can potentially pass. Leakage, however, is the actual flow of fluid through that opening. Let's look at a practical example. Imagine a pressure vessel has a tiny crack. The crack exists, therefore a leak exists. But suppose both sides of the crack are at exactly the same pressure. Will fluid flow? No. Without a pressure differential, there is no driving force. Therefore, leak exists. Leakage does not. This distinction appears repeatedly in certification exams. Let's repeat it. Leak equals hole. Leakage equals flow. Leak equals physical defect. Leakage equals actual fluid movement. If you remember only one thing from this slide, remember that. Many inspectors fail questions because they do not clearly separate these two definitions. Before we understand leak testing, we must understand pressure. Pressure is defined as force divided by area. P equals F/A. This equation is simple but extremely important. Now let's understand where pressure comes from. At the microscopic level, atoms and molecules are constantly moving. They collide with each other. They collide with surfaces, and these countless collisions generate force. The total force acting on a surface creates pressure. Now here's an interesting question. What happens when temperature increases? The molecules move faster. Faster molecules create more collisions. More collisions create higher pressure. This relationship is extremely important in leak testing. Now let's discuss vacuum. Many people think vacuum means empty space. That is not completely correct. A vacuum simply means pressure below atmospheric pressure. A perfect vacuum is practically impossible. No matter how good your vacuum pump is, some molecules will always remain. Now here's the most important concept. Fluid always moves from high pressure to low pressure. That statement explains almost every leak testing technique. Whether you are using bubble testing, pressure change testing, tracer gas testing, or mass spectrometry, the entire principle depends on pressure differential. No pressure differential, no leakage. Remember that. Now let's explore something fascinating. Why do leaks occur? At first glance, solid materials appear completely solid. Steel appears solid. Aluminum appears solid. Plastic appears solid. But at the atomic level, things are very different. Every material contains microscopic pathways. Every material contains imperfections. Every material contains spaces between atoms. This means that given sufficient pressure differential and enough time, fluids can migrate through extremely small openings. Now let's talk about helium. Helium plays a critical role in advanced leak testing. But why helium? Why not oxygen? Why not nitrogen? Why not hydrogen? The answer lies in atomic properties. Helium is extremely small. It moves easily through tiny openings. It is inert. It is non-toxic. It is non-flammable. And its atmospheric concentration is extremely low, only about 5.2 parts per million. This makes helium ideal as a tracer gas. Think about a helium balloon. Have you ever noticed how it slowly shrinks over time? The balloon may appear intact, yet helium atoms gradually escape through microscopic pathways. That same principle allows helium leak detectors to identify extremely small leaks that other techniques may never detect. And this is exactly why helium became the industry-standard tracer gas for mass spectrometer leak testing. Now let's look at the 4 major leak testing techniques every inspector must know. Number 1. Bubble leak testing. This is the oldest method. Simple. inexpensive, easy to perform, but relatively low sensitivity. Number 2. Pressure change testing. This method monitors pressure changes over time, useful for determining whether leakage exists, but it cannot identify the exact leak location. Number 3. Halogen diode testing. This uses tracer gases and detector probes, higher sensitivity, capable of locating leaks, but requires specialized equipment. Number 4. Mass spectrometer leak testing. The highest sensitivity technique. Uses helium tracer gas, capable of detecting extremely small leakage rates. Widely used in aerospace, nuclear, semiconductor, and high-integrity systems. Now here is a classic exam question. Which leak testing method provides the highest sensitivity? Most candidates immediately answer, mass spectrometer testing. And generally that is correct. However, some examination questions are worded differently and emphasize application requirements. Always read every answer carefully before selecting your response. Many candidates lose marks not because they lack knowledge, but because they rush through the question. And that's exactly the kind of mistake we want to avoid.
Now, inspectors, let's begin with the oldest leak testing method ever used in industry: bubble leak testing. Even though this technique is simple, don't underestimate its importance. Today, bubble testing is still widely used in pressure vessel fabrication shops, piping systems, storage tanks, heat exchangers, boiler components, and field construction projects. The principle is straightforward. A pressure differential exists across the component. If gas escapes through a leak and passes through a liquid or soap solution, bubbles become visible. And those bubbles indicate leakage. Now let's look at the two common methods. The first is immersion testing. The component is submerged in water. Air or gas pressure is applied internally. If leakage exists, bubbles rise to the surface. The second method is soap solution testing. Instead of immersing the component, soap solution is applied directly to welds, flanges, nozzles, threaded connections, or suspected leak locations. Any escaping gas forms visible bubbles. Now let me give you a practical example. Imagine you're inspecting a newly fabricated air receiver tank. The tank is pressurized to the test pressure. Soap solution is applied around nozzle welds. Suddenly, tiny bubbles begin forming at one location. That indicates a leak path exists. Simple, effective, low cost. Now let's discuss the biggest limitation. The detector is the human eye, and human eyes are not perfect. Poor lighting, fatigue, distractions, blinking, all can result in missed indications. This is why bubble testing has lower sensitivity compared to advanced leak testing methods. Interview question: what is the oldest leak testing technique? Pause for a moment. The answer is bubble leak testing. Level 2 exam trap. What is the major limitation of bubble testing? Many candidates answer low sensitivity. That is partially true. But the textbook answer is often human error. Specifically, visual detection limitations. Remember that. Many inspectors think modern equipment makes bubble testing obsolete. That is completely wrong. In reality, bubble testing remains one of the most commonly used leak testing methods worldwide. Now let's move to pressure change testing. This method is elegant because it does not require tracer gases. It does not require sophisticated detectors, and it does not require direct leak visualization. Instead, it relies on pressure monitoring. Here's how it works. A vessel is pressurized. A calibrated gauge monitors internal pressure over time. If pressure decreases unexpectedly, leakage may be occurring. For vacuum systems, the opposite occurs. The vessel is evacuated. Pressure is monitored. If pressure rises, atmospheric air is entering through a leak. Now let's look at a refinery example. Imagine a pressure vessel is isolated after hydrotesting. The vessel is pressurized using nitrogen. The pressure gauge initially reads 10 bar. After several hours, the pressure drops to 9.5 bar. Assuming temperature remains stable, this pressure loss suggests leakage. The method has successfully detected leakage. But here's the important question. Do we know where the leak is? No. And that is the biggest limitation. Pressure change testing tells us leakage exists. It does not tell us where. Think of it like a medical thermometer. The thermometer can tell you that you have a fever, but it cannot tell you the exact cause. Pressure change testing works the same way. Common interview question. Can pressure change testing locate the exact leak position? The answer is no. It only confirms leakage. Another technique is required for leak location. Exam trap. Many students incorrectly assume pressure change testing is both a detection and location method. It is not. Detection only. Remember that distinction. Field tip. Always account for temperature variations. A pressure drop caused by cooling may not indicate leakage. This is a common field mistake made by inexperienced inspectors. Now let's move into more advanced leak testing territory. Halogen diode leak testing. This method uses a halogen tracer gas. Historically, freon-based gases were commonly used. The detector contains a sensing element capable of identifying the tracer gas. This technique is often called sniffer testing because the detector probe literally searches for escaping tracer gas. Let's look at the pressurized system configuration first. The component is pressurized using halogen tracer gas. The inspector moves the detector probe around welds, joints, seals, and connections. If tracer gas escapes through a leak, the detector responds. Now let's look at the vacuum configuration. The component is evacuated. Tracer gas is introduced externally. The vacuum system pulls the tracer gas through any leak. The detector identifies the incoming gas. This configuration is particularly useful for sealed systems. Practical example. Imagine a refrigeration system. The system contains refrigerant. A leak is suspected. The technician uses a sniffer probe around joints and fittings. The detector alarm activates near one fitting. Leak located. That's halogen diode testing in action. Important exam point detector probe. Sniffer probe. These terms often refer to the same device. Exam questions frequently test this terminology. Interview question. Why is halogen diode testing more sensitive than bubble testing? Because electronic detection can identify smaller leakage rates than human visual observation. Retention hook. Many inspectors confuse leak detection with leak measurement. Halogen testing can often do both. Depending on calibration, it may provide quantitative leakage information as well. Now, inspectors, we arrive at the king of leak testing techniques, mass spectrometer leak testing. This is the highest sensitivity leak testing method discussed in this chapter. And if you remember only 3 words, remember these. Mass spectrometer. Helium. Highest sensitivity. Let's understand how it works. The test component is usually evacuated. Helium tracer gas is introduced outside the component. If a leak exists, helium enters through the leak path. The mass spectrometer identifies helium atoms based on their atomic mass. Because helium concentration in normal atmosphere is extremely low, the detector can easily distinguish tracer helium from background gases. This allows detection of extremely small leaks, far smaller than bubble testing, far smaller than pressure change testing, and typically more sensitive than halogen methods. Why helium? This question appears frequently in exams. Helium is inert, non-toxic, non-flammable, small atomic size, low atmospheric concentration. All of these characteristics make helium ideal for leak testing. Practical aerospace example. Imagine a spacecraft fuel system. Even microscopic leakage could be catastrophic. Bubble testing would not be sensitive enough. Pressure change testing may not detect tiny leaks. Mass spectrometer testing becomes the preferred solution. Common interview question. Why not use hydrogen since it is smaller than helium? Excellent question. Hydrogen is highly flammable and potentially explosive. Helium provides excellent sensitivity while maintaining safety. Exam memory shortcut. Mass spectrometer equals helium. Helium equals highest sensitivity. Highest sensitivity equals mass spectrometer. Keep repeating that relationship. It appears everywhere in certification exams.
Now that we understand the techniques, let's answer a bigger question. Why do industries spend millions of dollars every year on leak testing? Because leaks create consequences, and those consequences can be severe. Let's discuss the 3 primary reasons. Reason number 1, prevent material loss. Every leak represents lost product. In a refinery, leaking hydrocarbons mean lost revenue. In a gas processing facility, leaking natural gas means reduced efficiency and profit. In pharmaceutical manufacturing, leakage can result in expensive product contamination. A tiny leak operating 24 hours a day can become a major financial loss over time. Reason number 2, safety. This is perhaps the most important reason. Imagine a hydrogen leak, an ammonia leak, a chlorine leak, or hydrogen sulfide leakage. The consequences can include fire, explosion, toxic exposure, environmental contamination, and loss of life. This is why leak testing is a critical safety activity, not merely a quality control exercise. Reason number 3, reliability. Leak testing identifies components that cannot perform their containment function. Pressure vessels, heat exchangers, valves, piping systems, aerospace components, all must maintain containment integrity. Leak testing helps ensure they do. Real field story. Imagine a heat exchanger tube with a microscopic leak. Initially, everything appears normal. Over time, process fluids begin mixing, efficiency drops, contamination occurs, unexpected shutdown follows. A leak that seemed insignificant becomes a major operational problem. This is exactly why leak testing exists, to find problems before they become failures. Level 2 exam question. What is the primary purpose of leak testing? Answer: to prevent material loss, ensure safety, and verify system reliability, not simply to find holes. End of section transition. Now that we've covered the major leak testing methods and understood why leak testing is so important, the next section will focus on something every Level 2 and Level 3 candidate must master. How do we actually locate leaks? How do we select the correct technique? How do we measure leakage rates? And what is the difference between static and dynamic leak testing? These concepts are where many candidates struggle. So in Part 3, we're going much deeper into the practical decision-making process used by professional inspectors in the field.
Now, inspectors, we are entering one of the most practical sections of leak testing. Many students think finding a leak is the same as measuring a leak. It is not. And this misunderstanding causes many exam failures. The first question an inspector must ask is, do I need to locate the leak? Do I need to measure the leakage rate? Or do I need both? This decision determines which leak testing technique should be selected. Let's start with a pressurized system. Imagine a pressure vessel operating at 15 bar pressure. gas inside the vessel wants to escape. If we use a detector probe on the outside surface, we can search for escaping tracer gas. The detector responds when it encounters the leaking gas. This allows us to locate the leak. Now consider an evacuated system. Pressure inside the vessel is lower than atmospheric pressure. Tracer gas is applied externally. The vacuum inside pulls tracer gas through any existing leak. The detector identifies the incoming gas. Again, the leak can be located. Notice something important. The direction of fluid movement depends entirely on pressure differential. High pressure always moves toward low pressure. This principle never changes. Practical boiler example. Imagine a boiler superheater header that has undergone repairs. The client suspects leakage near a welded attachment. The header is pressurized with tracer gas. The inspector uses a detector probe around all welds. At one location, the detector signal increases sharply. Leak located. Repair can now be performed. Common interview question. Which method is generally faster for leak location? The answer is tracer gas testing in evacuated systems, because gases move rapidly toward low-pressure regions. Level 3 exam trap. Many candidates assume leak testing always identifies the exact location. Wrong. Some methods only indicate that leakage exists. Location and measurement are separate objectives. Always determine which objective the client requires. This slide is extremely important for Level 3 candidates. Because Level 3 examinations focus heavily on technique selection, let's imagine a client asks, which leak testing method should we use? A beginner may answer, use the most sensitive method. But a Level 3 inspector knows that is not the correct approach. Technique selection depends on multiple factors. Let's discuss them one by one. Factor 1. Leak size. What is the smallest leak that must be detected? A bubble test may be sufficient for a large leak. A semiconductor vacuum chamber may require helium mass spectrometry. Sensitivity requirements drive technique selection. Factor 2. Accuracy. Do we need a simple yes or no answer, or do we need an exact leakage rate? Some applications require quantitative measurements. Others only require leak detection. Factor 3. Accessibility. Can the component be immersed? Can the probe reach all surfaces? Can the vessel be evacuated? Physical access often limits technique selection. Factor 4. Operating conditions. Temperature, pressure, fluid type, environmental conditions, all influence testing decisions. A technique that works perfectly in a fabrication shop may be impossible in an operating refinery. Factor 5. Hazards. Safety always comes first. Some tracer gases may present environmental concerns. Others may require special handling procedures. Never ignore safety when selecting a method. Factor 6. Production volume testing. One pressure vessel is very different from testing 10,000 automotive components. High-volume manufacturing often requires automation and speed. Real industry example. Imagine two projects. Project 1. A small workshop fabricating compressed air receivers. Project 2. A spacecraft manufacturer producing fuel system components. Will they use the same leak testing technique? Absolutely not. The risk levels are completely different. This is why technique selection is always application dependent. Level 3 exam trap. Do not choose techniques based only on sensitivity. Consider cost, accessibility, safety, production requirements, and acceptance criteria. This is exactly how Level 3 questions are designed. Now let's discuss leakage rate. And this is where leak testing becomes more scientific. Many students think a leak either exists or does not exist. In reality, leakage can be measured. and leakage rate is one of the most important concepts in advanced leak testing. Let's start with minimum detectable leakage. This refers to the smallest leakage rate that a particular technique can reliably detect. Every leak testing method has a limit. Below that limit, the leak becomes invisible to the method. Now let's discuss what controls leakage rate. Several factors are involved: leak geometry, fluid properties, pressure differential, temperature, and flow characteristics. Let's focus on pressure differential. This is critical. Suppose you have the same leak, exactly the same hole. Now increase the pressure difference across that hole. What happens? Leakage rate increases. The hole did not change. The pressure differential changed, and therefore the leakage rate changed. This concept appears frequently in examinations. Practical refinery example. Imagine a small pinhole in a heat exchanger tube. At 5 bar differential pressure, leakage may be minimal. At 20 bar differential pressure, leakage could increase dramatically. Same leak, different leakage rate, because pressure differential changed. Key definition: pressure boundary. This is the wall separating internal and external environments. Leakage occurs across this boundary. Pressure vessels, heat exchanger tubes, piping, storage tanks, all contain pressure boundaries. Common interview question: can the same leak produce different leakage rates? Yes, because leakage rate depends heavily on pressure differential. Retention hook. Many inspectors focus only on leak size. Professional inspectors focus on leakage rate, and there is a significant difference. Now let's classify systems. In leak testing, systems are commonly divided into open units and sealed units. Let's start with open units. Open units allow access to both sides of the pressure boundary. These systems are generally easier to evaluate. The inspector can choose whether to evacuate one side, apply tracer gas, use dynamic testing, or use static testing. Open access provides flexibility. Now let's discuss sealed units. Sealed units are more challenging, because direct access to both sides may not be possible. The first question we ask is, does the system already contain a tracer gas? This is called an inherent tracer gas. For example, some systems naturally contain gases that can be used during leak testing. If an inherent tracer gas exists, testing becomes simpler. If not, alternative methods must be selected. Practical example. Imagine a sealed refrigeration component. The refrigerant itself may act as a tracer gas. No additional tracer gas may be required. This can save significant time and cost. Air-sealed systems. Now consider systems leaking directly into atmosphere. These systems often require higher sensitivity techniques. Back-pressuring may be necessary. Additional test setup may be required. Again, technique selection depends on application requirements. Important exam point. Leakage rate measurement does not tell you how many leaks exist or exactly where they are located. It only tells you how much leakage is occurring. Many students confuse these concepts. Don't be one of them. Now let's finish this section with something extremely practical. The proper leak testing sequence. This is how experienced inspectors approach real-world leak testing projects. Not only in fabrication shops, but also in refineries, power plants, petrochemical facilities, and aerospace manufacturing. Let's go step by step. Step 1. Gross leak detection. Always start with less sensitive methods. Bubble testing, pressure change testing, simple techniques. The objective is to identify major leakage quickly. There is no point using extremely sensitive equipment if a massive leak already exists. Step 2. Repair gross leaks. Once major leaks are identified, repair them. Document all repairs. Verify repair quality. Then proceed. Step 3. Overall leakage measurement. Measure total system leakage. Determine whether leakage remains within acceptable limits. This provides an overall assessment of system integrity. Step 4. Sensitive leak location. Now introduce advanced methods: tracer gas testing, sniffer probes, mass spectrometer techniques. Locate remaining small leaks. Step 5. Repair individual leaks. Each identified leak should be repaired whenever practical. Documentation is essential. Traceability is essential. Quality control is essential. Step 6. Final acceptance testing. This step is frequently overlooked by inexperienced personnel. After repairs, repeat leakage measurement. Confirm compliance with acceptance criteria. Never assume repairs were successful. Verify. Always verify. Real field example. Imagine a pressure vessel undergoing final inspection. A large nozzle leak exists. If you immediately perform helium mass spectrometer testing, the gross leak overwhelms the system. Time is wasted. Money is wasted. Instead, first identify and repair gross leaks. Then proceed to higher sensitivity techniques. This is why sequence matters. Common interview question. Why should gross leaks be repaired before performing highly sensitive leak testing? Because large leaks can interfere with sensitive measurements and waste inspection time. Level 3 Exam Trap. Many candidates jump directly to the most sophisticated technique. That is not how professional inspectors work. Always start with gross leak detection, then progressively increase sensitivity as required.
All right, inspectors, before we move into the quiz section, let's perform a complete chapter review. This is the stage where information moves from short-term memory into long-term memory. And this is exactly where successful certification candidates separate themselves from average candidates. Let's review the entire chapter together. Leak testing is concerned with the flow of liquids or gases from a pressurized containment system or into an evacuated containment system. Remember this definition. It appears everywhere. Now let's revisit the most important exam trap. A leak is the physical opening. A crack. A pinhole. A crevice. A fissure. Leakage is the actual movement of fluid through that opening. No fluid movement? Then leakage does not exist. Even if the leak exists. Now let's review pressure. Pressure is force divided by area. Again. P equals F/A. Pressure exists because molecules are constantly moving and colliding with surfaces. More collisions mean higher pressure. Higher temperature means faster molecules. Faster molecules mean more collisions. More collisions mean greater pressure. Now let's discuss vacuum. Vacuum is simply pressure below atmospheric pressure. A perfect vacuum is practically impossible. Some molecules always remain. Remember this because exam questions often try to trick students into thinking perfect vacuum can be achieved. It cannot. Now let's review the 4 major leak testing methods. Bubble testing. Pressure change testing. Halogen diode testing. Mass spectrometer testing. Each method has advantages and limitations. Technique selection depends on application requirements. Not just sensitivity. This is a very important level 3 concept. Finally, remember. Static leak testing equals sealed chamber. No pumping. Dynamic leak testing equals active pumping. If you see the word pumping, think dynamic testing. That association will save you marks during examinations.
Now let's test your understanding. I want you to pause after each question and answer before I reveal the solution. This is exactly how I train Level 2 and Level 3 candidates. Let's begin. Question number 1. What is the primary purpose of leak testing? A. Report leaks to environmental agencies. B. Prevent material loss and ensure safety and reliability. C. Calculate financial losses. D. Install pressure relief devices. Pause now and think. The correct answer is B. Leak testing exists primarily to prevent material loss, improve safety, and verify reliability. Question number 2. Which leak testing method is generally considered the most accurate and sensitive? A. Bubble testing. B. Pressure change testing. C. Halogen diode testing. D. Mass spectrometer testing. Pause and think. The answer is D. Mass spectrometer testing. This technique uses helium tracer gas and provides extremely high sensitivity. Question number 3. A component contains a crack but no fluid is flowing through it. What exists? A. Leakage only. B. Leak only. C. Both leak and leakage. D. Neither. Pause and think. The answer is B. A leak exists, but leakage does not, because no fluid movement is occurring. Question number 4. Which leak testing condition requires pumping action? A. Open unit testing. B. Static testing. C. Sealed unit testing. D. Dynamic testing. Pause and think. The answer is D. Dynamic leak testing. Remember, dynamic equals pumping. Static equals no pumping. Trainer tip. If you answered all 4 correctly, you're understanding the chapter well. If not, revisit the earlier slides before moving on.
Now let's go deeper. A professional inspector doesn't simply memorize answers. A professional inspector understands why the answer is correct. Let's review. Underscore 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 underscore. Question 1. Difference between leak and leakage. Many students memorize the answer but fail to understand it. The leak is the physical defect. The leakage is the actual flow. Without fluid movement, leakage does not exist. This distinction appears repeatedly in certification exams. Underscore 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 underscore. Question 2. How is pressure created? Pressure is created by molecular motion. Atoms and molecules continuously collide with surfaces. Those collisions create force. And force acting over area creates pressure. This is fundamental physics. And it directly explains why leak testing works. Underscore 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 underscore. Question 3. Major limitation of bubble testing. The textbook answer is human error. Why? Because visual observation is required. Lighting. Fatigue. Attention span. Blinking. All influence detection capability. This is why advanced leak testing methods often use electronic detection systems. Underscore 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 underscore. Question 4. Why isn't mass spectrometer testing always the correct answer when discussing sensitivity? This is one of the most deceptive Level 3 exam traps. Technically, mass spectrometer testing is extremely sensitive. However, some questions emphasize application requirements. And the correct answer may be that sensitivity depends on the specific application. Always read every answer choice carefully. Never assume. Underscore 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 underscore. Question 5. Why is helium used? Because helium is small, inert, safe, non-flammable, and present in very low atmospheric concentrations. These properties make helium ideal for tracer gas applications. Now let's discuss the mistakes that cause candidates to fail examinations. Pay close attention. These are real mistakes I've seen repeatedly during training programs. Underscore 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 underscore. Trap number 1. Confusing leak and leakage. Let's say it again. Leak equals hole. Leakage equals fluid flow. If you mix these definitions, you will lose marks. Underscore 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 underscore. Trap number 2. Assuming pressure change testing locates leaks. It does not. Pressure change testing tells us leakage exists. It does not identify the location. This is one of the most common examination traps. Underscore 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 underscore. Trap number 3. Choosing techniques based only on sensitivity. This is classic Level 3 material. Technique selection must consider sensitivity, cost, accessibility, safety, environmental conditions, production requirements, and acceptance criteria. Sensitivity is only one factor. Underscore 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 underscore. Trap number 4. Assuming helium mass spectrometer testing is always the correct answer. Read the question carefully. The examination may be evaluating application requirements rather than absolute sensitivity. This distinction matters. Underscore 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 underscore. Trap number 5. Confusing static and dynamic testing. Remember this shortcut. Static equals no pumping. Dynamic equals pumping. If you remember nothing else, remember that. Underscore 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 underscore. Trainer advice. Examiners rarely test simple memorization. They test understanding. When answering questions, always ask yourself, why is this answer correct? That mindset dramatically improves exam performance. Excellent work, inspectors. We've reached the end of Chapter 7. Now let's perform one final rapid revision. I want you to answer mentally as quickly as possible. Ready? Let's begin. What is leak testing? The flow of liquids or gases through a containment boundary. What is a leak? A physical opening. What is leakage? Actual fluid flow. Pressure formula. P equals F/A. Oldest leak testing method? Bubble testing. Highest sensitivity technique? Mass spectrometer testing. Preferred tracer gas? Helium. Atmospheric helium concentration? Approximately 5.2 parts per million. Pressure change testing can do what? Detect leakage. Can it locate leakage? No. Static testing? No pumping. Dynamic testing? Continuous pumping. Why perform leak testing? Safety. Reliability. Material conservation. Environmental protection. And regulatory compliance. Underscore 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 underscore. Final motivation. Before we conclude, remember something important. Leak testing is not just another NDT method. It is a method that protects people, protects equipment, protects the environment, and protects entire industrial operations. A tiny leak today can become a catastrophic failure tomorrow. That is why skilled inspectors are valuable. Because they identify problems before those problems become disasters. Continue reviewing these concepts. Practice the quiz questions. Study the exam traps. And most importantly, understand the principles, not just the answers. Thank you for joining this Chapter 7 leak testing training session. I hope you found it valuable. If you're preparing for ASNT, PCN, ISO 9712, or employer qualification examinations, keep learning, keep practicing, and keep improving. I'll see you in the next chapter of our NDT professional training series. Stay safe. Stay curious. And keep inspecting with confidence.